Okay, good day. This is Math 140 College Algebra. I am Professor McCully, and this is lesson 5.2, Rational Functions and Asymptotes. So let's get right to it. Today we're going to find the domains of rational functions, and then we're going to find the horizontal and vertical asymptotes of rational functions. So we know domain is your favorite thing, but before we get to that, we will definitely review the definition of a rational function. A rational function f of x is a function that can be written in the form f of x is equal to n of x over d of x, where both n of x and d of x are polynomial functions, and d of x is not equal to 0. The domain rules are still the same from Algebra 2. We always start with all real numbers, and then we got to throw out any value for x that will cause a division by 0. That's going to be important for this particular lesson. Then we also have to throw out any value for x that causes the even root of a negative number or the logarithm of a negative number. And then we have to throw out any value for x that does not make sense in the context of the problem. And so the 1 and 3 is pretty much what we're going to be talking about today. The definition of a vertical asymptote: the line x equals a is vertical asymptote of the graph of f if f of x goes to infinity or f of x goes to negative infinity as x goes to a either from the right or from the left. Definition of a horizontal asymptote: the line y equals b is a horizontal asymptote if the graph of the graph of f if as f of x goes towards b, x goes to positive infinity or x goes to negative infinity. And so just a real quick example of that, we can go to our graphing calculator. If we close that out, go to our y equals first, and I'm missing some stuff, so let's see if maybe pulling this back up will refresh. How about a refresh? Sorry about that, folks. Let's see here. It'll come right back up. There we go. Let's close this. Okay. And so just a real simple, that's from last time. Let's clear this out. Let's just go 1 divided by x, and then let's go parentheses x minus 2. All right, so here we have a vertical asymptote at x equals 2. And the reason that that ends up being is because we have a division by 0. And the domain of this thing is all real numbers except for x equals 2. And if we go to our graph here, let's open my window. Let's go start at 1, go by 1s, turn to auto. Real quick, you can see I have an error at x equals 2. There's my undefined, because again, you can't divide by 0. And we also have a vertical asymptote for this particular one. Or a horizontal asymptote, if I hit my graph again, you'll see that as x goes to positive infinity and as x goes to negative infinity, this function tends to look closer and closer to the line y equal to 0, or what we normally call the x-axis. All right. Finding vertical asymptotes. The vertical asymptote of a rational function can occur at any non-reducible 0 of the denominator. Any 0 of the denominator is any 0 of the denominator. This is not also, I think that should say that is not. So let's change that. That'll make more sense if I go that. Any 0 of the denominator, that is not also 0 of the numerator. So what does that mean in context? So if let's say I said f of x was equal to x plus 2 divided by x plus 2 over x minus 2. And so you'll notice I call the vertical asymptote at a non-reducible 0 of the denominator. Now this denominator has 2 zeros. All right, the denominator has a 0 at x equals negative 2 and x equals positive 2. Since the numerator also has A0 at -2. -2 is a reducible 0. And at +2, we have a non-reducible 0. Now, what does that mean? Well, if I go to my graphic calculator again, hit my y equals, we clear this out. We're going to go with an actual fraction so we can see it. And we'll go, we had x plus 2 over x plus 2 times x minus 2. Oops, I got cosine. I don't want cosine in there. Let's hit the delete button there, and we'll go insert a parenthesis, and hopefully that'll work. Okay, that looks like it's going to be okay. And again, these two factors, x plus 2 on the top and x plus 2 on the bottom, reduce. It has a 0 at -2, so when I look at the graph, you'll notice here at -2, I don't have a vertical asymptote because it reduced. At x equals 2, I have a vertical asymptote because it does not reduce. Now, if I look at my table, all right, let's go up here. At both -2 here and at +2 here, we still have the error, but on the graph, because the x minus 2 didn't reduce with the numerator, I get a vertical asymptote. Because the x minus 2 or x plus 2 reduced with the numerator, I don't get a vertical asymptote. There's actually a hole there. All right, so finding horizontal asymptotes. To find a horizontal asymptote of a rational function, you compare the degree of the numerator, n, to the degree of the denominator, d, and apply the following 3 rules. If n is bigger than d, then there is no horizontal asymptote. If n is less than d, then the horizontal asymptote is y equal to 0, or the x-axis. And if n equals d, then the horizontal asymptote is the ratio of the leading coefficients. All right, so let's go back to this particular one that I just did. The degree of the numerator would be 1 because I have an x to the first. If I multiplied this out, I'd have x squared as my leading term, and therefore the degree of the numerator 1, the degree of the denominator 2. I would have a situation where the degree of the denominator was bigger than the degree of the numerator, so the horizontal asymptote is y equal to 0. And in our graph, we see that y equals 0 is our horizontal asymptote. So that's a simple example for that. So as a quick example here, we're going to find the horizontal and vertical asymptotes and any holes in the following function, and we're going to state the function as domain and its range. All right, so the first thing I want to say is factor this thing, both the numerator and the denominator. And the only thing that's common here is an x. So this thing factors to x times x minus 4. And this is a difference of squares. So I've got x minus 2 times x plus 2. And I'll notice that I have no factors in the numerator that cancel with factors in the denominator. So I will have 2 vertical asymptotes at x equals 2 and x equals -2. And then if I want to talk about the horizontal asymptote, there's only one horizontal asymptote here. And again, we're going to apply these rules. The numerator was 2, the denominator was 2, so the horizontal asymptote is the ratio of the leading coefficients. Okay, so the leading coefficient of the numerator is 1, the leading coefficient of the denominator is 1, so 1 horizontal asymptote at y equals 1. Now, we should check that. And so if I go to my y equals and I clear, well, let's just clear. Let's see if I can, oh, that's beauty. Okay, so x squared minus 4, oops, minus 4x, y equals minus 4 x, and then I go down arrow, and I clear out the bottom, and I have x squared minus just 4. And when we look at the graph of that, notice at -2 and at +2, I have vertical asymptotes. And then if I go down here to my y equals to 1, and I hit graph there, you can see that this function is going to tend to go towards that y equals 1, and this function here is going to tend to go to y equals 1. So that's my horizontal asymptote. There are no holes in this, but if I wanted to do the domain, all reals, where x is not equal to plus or minus 2, and the range, the only value, actually, in this one, even though we have a horizontal asymptote at 1, because of this little blip here, we actually touch 1. So this one's going to be all reals. All right, moving on. It says find the horizontal and vertical asymptotes and any holes in the following function, then state that the function's domain and range. So again, I'm going to say I'm going to factor this thing. This top polynomial is a perfect square polynomial. It factors into x plus 1 times x plus 1. And then the bottom one, let's see here. I'm going to want +2 and -3. So I'm going to go 2x minus 3 and then x plus 1. So 2x times x gives me 2x squared. 2x times 1 is 2x. -3 times x is -3x, plus the 2x gives me -1x. The -3 times 1 is -3. So those are my factorizations there. And I clearly see that I have one of these factors in the numerator and the denominator that cancels out. So I'm going to have a vertical asymptote at x equals, and this thing doesn't cancel with anything in the numerator, so it's going to cause the vertical asymptote. And so if you can't tell exactly what makes that 0, figure out what makes it 0. You go 2x minus 3, you set it equal to 0, and figure out what value for x makes this thing equal to 0. 2x equals 3, x equals 3 over 2, so I have a vertical asymptote at x equals 3 over 2. Now, this factor here, because it cancels out, means that I am not going to have a vertical asymptote there, but it is still undefined, so I'm going to have a hole at x equals -1. And then the domain will be all reals, where x is not equal to -1 or 3 over 2. And then my range, I think it's also going to be all reals, but let's not do that. I think it's still going to be all reals, but let's check. Let's graph this thing. So let's go to our y equals, and we'll clear this out. And on the top, we have x squared, and then it was minus x, and then it was plus 3 on the top, and then on the bottom, we had, what do we have on the bottom there? X squared, that's wrong. So x squared plus 2x plus 1. So I need to fix that. So x squared plus 2x plus 1. And then on the bottom, we had 2x squared. Oops, too many x's there. Let's delete that. 2x squared minus x. And then it was minus 3. Let's check to make sure. Yep. And so when I go to graph this thing, certainly it looks like I have my vertical asymptote at the 3/2, so 1.5. And it looks like I have a horizontal asymptote that it doesn't cross. And so what is my horizontal asymptote going to be? a horizontal asymptote. Well, I got x squared over x squared, so the degrees are the same. So the ratio of the leading coefficient is going to be y equals, the leading coefficient of the numerator is 1, the leading coefficient of the denominator is 2, so I'll have a horizontal asymptote of y equals half, and then the range will be all reals where y is not equal to 1/2, and that's my answer for that. All right, let's see here. Another example, Mr. McCully is raising wild widgets in a pond in his backyard. The number of wild widgets in the pond after he introduces the first batch of widgets can be modeled by the function w of t equals 1600t plus or over t plus 400, where w is the number of widgets and t is the time in months. How many widgets are introduced to the pond initially? Okay, so that's pretty simple. We're going to find out when t equals 0. So w of, and let's do that again. So we're going to find w of 0. And so I've got 1600 times 0 over 0 plus 400. That's not very good because I get 0 over 400, so there's 0 then. Poorly written question, 0 widgets. I should have put like a +1 or something over there. That's okay. How many widgets are in the pond a year after the production? T is the time in months. So since T is the time in months and we want 1 year, B will be W of 12 equals 1600 times 12 over 12 plus 400. And let's see here. We'll calculate that real quick. 1600 times 12 divided by 412. I can do that in my head. And so we get 47-ish widgets. And the maximum number, well, what is the maximum number going to be? And so again, we have this equation, W equals 1600 times T over T plus 400. Now, basically what we're trying to figure out is what happens as W goes, or not W, as T goes to infinity, because T is our x-axis. All right, well, as T gets big, this number gets very big, and this number gets very big. We get something infinity over infinity, and that shouldn't be 1,000. I'm sure you're seeing me make mistakes, but we'll get it right. So I have no real recourse but to apply the horizontal asymptotes rules to this thing. And so I have a linear equation on the top, I have a linear equation on the bottom. The degree is 1, the degree is 1, so it should be a ratio of the leading coefficients. So as t goes to infinity, the ratio of the leading coefficients, W goes to 1600 over 1, which is 1600 widgets. All right, well, that's all I got for you today, folks. So the Marvel fun fact of the day: in Spider-Man Far From Home, on Peter's passport, he has a birthday of August 10th. Spider-Man's first appearance was Amazing Fantasy number 15, and it was released on August 10th, 1962. There's your Easter egg for the day. Have a good day, folks. Bye.